So, Daniel, how are you? Is it? Yes, the physical yesterday is translating my book in English. Yes, very good idea. I had an email from one neighbor who said she couldn't come. Yes. Even tonight, that's for dinner. And next week we will be coming to the NRPB symposium. So we'll be there. Do I get more money? Yes. I was joking. Every time I sign. I like this.
各位女士、各位先生，我们要开始今天的一个special lecture。那个同仁可能他们如果开始之后进出可以从后门哈。所以give me pleasure to introduce our special guest, our speaker today, Professor Bertrand. He has been a long-term friend to Taiwan in supporting from the era of conducting the national research program on genetic medicine, and then now the NRPB. He is a very famous scientist in the field, and also he has deep humanity and social science concern. So he's also acting as our ELSI director of the entire Human Genome Program, and then later the NRPB program. And I personally has been given this privilege to discuss and also co-publish some paper with him. We wrote one article on autism, the French story, and also the ethical, legal, and social impact concerns long ago. But still, we are receiving advices and also very good guidance from him. And Professor Jordan, he is currently the NRRS Erasmus Research Director, though he retired. And he also has been in charge of the Marcelli mice genome pool research. And currently, he is the counselor of our NRPB program. So today, his talk will be ELSI issues in clinical new generation sequencing. Let's welcome Mr. Jordan. Before I give this microphone to him, I also like to introduce two special guests. Okay, one is Professor Jim Dwyer. He is a visiting professor to the Department of Social Medicine. He has been here for 1 year as a visiting professor. He teaches medical ethics and cooperates with us in many research programs. Okay, this is Jim. And the other one, we might be surprised, is Mr. I know your name in Chinese, Lin. Okay, he's a journalist. Okay, Lin Changhong. So in Japanese is Masahiro Hayashi. So he's a journalist, yes, and he is also a fan to Professor Jordan. He has translated his 2 books from French to Japanese. Okay, and then he flew from Japan this morning, especially to join this meeting. So let's give him a warm welcome.
Thank you very much, Daniel, for giving me this opportunity, and also giving me the opportunity to meet my Japanese translator, which is a big pleasure. Yes, so every year I come to Taiwan, every year I have a discussion with the ELSI people, with you, on a topic of current interest. So given the development of new generation sequencing, I thought this would be an interesting topic for you. So of course I am not an ELSI person. I have some interests in the field, but I'm not a specialist. So really my talk will be probably two-thirds telling you what's going on with new generation sequencing, and one-third discussing the issues it raises in terms of ethics. So it's not really a 100% ethics talk. But I think given the way this is moving so fast, I think it's really useful to know where we stand today. So let's see if I can break this thing. Wrong button. Wrong button again. I want to move forward. These things can be temperamental. Let's see if this works. No.
Here.
It's not going to work. I think it's too far. Okay, I will stand on this side. Let's see. Yes. Now it works. Okay, so I'm starting, as I said, with an update on new generation sequencing, NGS for short. Oops. Okay. Sorry. Okay. This is a map you can find on the internet. It's a site which gives you the number of new generation sequencing machines that have been installed worldwide. It's quite impressive because this was introduced maybe 4 or 5 years ago, and these machines are about $500,000 each. And as you can see, it has really made a lot of them have been sold now, being used of course in the United States, in Europe, and also in the East, in Asia. And if we zoom in a little, you see that you have quite a few actually in Taiwan. The figures on this side are not exact. I mean, it's underestimated because it's based on what people put on the site, and not everybody indicates. So there are more than that. But you can see, for example, that compared with Japan, Taiwan is doing quite well in terms of being involved in this new field. So, as we'll see, the increase in performance is so big that it's really opening up many new fields. And I think I have a close-up of the Taipei region, and you see a big cluster here, which corresponds, of course, to Academia Sinica and its satellites. Yeah. Okay. Okay. So that's
It's hard.
It's not working. I have to be close. It only works if I'm close to the gadget.
So maybe do this one.
Okay, thank you. Yeah, I mean, I gave talks in Tainan yesterday. It was the same problem, so it's not specific. So, as I said, this technology has really caught on, as you saw from the number of machines that are being used worldwide, and it has become essential in research, in academic research. It's actually replacing microarrays, which has been my pet subject for a few years. Not in all applications, but in many applications. And it's really opening up something which one might call sequence-based biology, a way of looking at biological systems in which you know that you can get any sequence, any amount of sequence of any organism very quickly and base a lot of conclusions on that. And it's also having an impact in clinical research, in working out monogenic diseases for which the gene was not known, in trying to understand what's going on in cancer, actually finding that it's even more complicated than we thought. But what I want to tell you about today is whether it's really now already being applied in clinical research, not in in clinical practice as a diagnostic in hospitals to treat patients. So next slide, please. Just a few words about the hardware, the machines. Next one. Even close by. So at this time, there's basically two classes of new generation sequencing machines. There are large systems, and as we see, there are smaller systems. So the large systems, there's essentially 3 or 4 major manufacturers who are competing very hard, which is part of the reason why the field is moving so quickly. And so these are machines that cost around $500,000 US, so pretty big pieces of equipment. But they are able, in just one run, which lasts a few days, they are able to read 500 gigabases of DNA, 500 billion bases of DNA, which translates, if you take into account the fact that you need to read several times to have reasonable accuracy, which means in just one run, one of these machines can read several human genomes. I mean, which is a tremendous change. I mean, if you remember that the Genome project lasted 10 years, costed several billion US, involved hundreds of labs all over the world just to read the human sequence once. Now with these machines, you can read 3 or 4 or 5 sequences in a week. And the cost is about $10,000 US for one run of these machines. So, which means a few $1,000s per genome, not a few $1 billion per genome, as only 10 years ago. Okay, so it's really such a change by several orders of magnitude, so really changes the picture. So these are the large systems, and now not the new generation, but a recent development is that now there are small machines which you can put on the bench top. Next slide, please. There's actually 3 currently on the market. They look more like this, fairly compact machines, which you can buy for 50 or 100,000 US dollars. So it's no longer a very big investment. They're also much faster. They do their run in 1 hour, 3 hours, 5 hours, depending on the machine. So you can get quick results. Of course, you get less sequence data, and it works out to be more expensive on the per megabase data, per megabase reckoning. But it's still much cheaper than the conventional sequencing. And it may be that these machines will actually open up the clinical field. I mean, that's can be debated, but anyway, this is a fairly recent development. And actually, development is still going on, as shown in the next slide. Now there is a next generation coming up, which is based on nanopores, so-called nanopores, where basically you manage to get the DNA to go through a membrane, and as the DNA goes through the membrane, you manage to read the bases one by one, and in this way you can get a lot more sequence, a lot cheaper, a lot faster. Several companies are developing this. One of them announces a gadget like this, which will supposed to cost $1,000, and which you plug into your computer and which reads a few megabases of sequence. It's a disposable device. So this may be true. It may come in 1 or 2 years from now. So it's still. The technology is definitely not stabilized. There is still a lot of progress going on, but people are using it a lot. Okay, next slide. So what about the clinic? Next slide. Sorry, I have many slides. So that's the question. This is a drawing I quite like, a cartoon I quite like. So it shows a patient who is not really feeling good, and his doctors who are reading his DNA sequence. So they have all his DNA sequence, all 3 or 6 billion nucleotides of it, and they cannot make much out of it. It's very interesting, but what use is it really for treating the patient? So that is the question. Are we already able to use this kind of information in the clinic? Next slide. So one can actually, there are indeed a number of current clinical applications, which one can put in 3 categories, if one likes. This one, full exome sequencing. I'll explain what exome is, mostly for mysterious cases where you're not able to find out what is wrong with the kid, although you're pretty sure it's a genetic disease. There is, of course, the cancer field, and there are a number of approaches applied in either in pediatrics or also for screening, preconception, or maybe pre-implantation. So I'll briefly describe these 3 applications and give 1 or 2 examples. Next slide. So this is an approach that has already been used in a few hospitals in cases where you have a child with a disease, which may be mental retardation, dysmorphism, whatever, muscular dystrophy, but you're not able to find out which is the defective gene. Maybe you have tried the most obvious possibilities, like Duchenne muscular dystrophy and a few others, and you have found no mutations. You don't know what's going on. And one approach that has been successfully used in a few cases is then to do full exome sequence, which means sequencing all the genes of this in the DNA of this individual. Not all the DNA, as you may remember, in human DNA, the genes themselves actually only occupy 1 or 2% of the DNA. There's a lot of junk DNA, so-called junk DNA, pieces of DNA between genes and within genes that play no obvious role. Most of the useful DNA is in the so-called exons, the expressed parts of genes. And there are now methods that work quite well and that are quite inexpensive to take a sample of DNA from a blood sample from a patient and extract from this DNA only the gene coding part, only the so-called exome, the sum total of all the exons. And of course, the advantage is that in that case, that means you have to sequence maybe 100 million bases instead of 6 billion bases. You reduce the amount of work by a factor of 100, just about. And so what can be done is to do this trick on DNA from the patient, then sequence this DNA very accurately, which means you read this DNA maybe 100 times so that you are almost sure that there is no remaining mistake, because of course the problem with all these techniques is that you have a certain percentage of mistakes. If you go over DNA many times, you minimize the number of mistakes. And then, of course, you have to do bioinformatics. Now you have the sequence of all 25,000 genes from this individual, and you use various methods to see if there's anything that might explain the condition. And I think the next slide shows one example. So yes, this was a small child with very severe autoimmunity problems. Well, they were thought to be autoimmune problems. He had fistulae, stomatal fistulae opening to the outside, making operations necessary. He had already been operated many, many times, and then the problem was continuing. So because this looked like an immune problem, so a number of genes to be involved in immune or autoimmune diseases had been tested, but no mutation had been found. And so finally, they decided to do whole exome sequencing to look at all the genes in one at a time. And handling this sequence data, they found indeed a mutation in a gene which is called XIAB, which is an inhibitor of apoptosis. So apoptosis is a mechanism by which cells commit suicide, if you want. And so an inhibitor of apoptosis is a molecule that prevents cells from committing suicide. And so you can imagine if this inhibitor is missing or is faulty, that you have the kind of symptom that this child presented. And since this gene was known to be expressed in blood cells, so this indicated that bone marrow transplantation, providing a different type of blood cell progenitor could help, and indeed this was performed, and the boy is doing well. So this is one case where the testing likely hypothesis one after the other did not provide the answer, and being able to do all of the 25,000 genes at one go gave you the answer. And of course this was completely impossible 5 years ago. Next slide is now cancer. So what is now, what quite currently being done is to not to look at the whole cancer genome, not to look at even at the whole cancer exome, but to focus on a few hundred genes that are already known to be often involved in cancer, in various types of cancer. In fact, we're finding out that there's not much specificity in each type of cancer. So you purify or amplify the coding part from 1, 2, or 300 genes that are already known to be often involved in various cancers. Again, you sequence this to high accuracy, and you look for known mutations or for unknown mutations in known genes. And there, what you hope to find is mutations in genes that code for proteins for which there is a drug already available, either already marketed or maybe undergoing clinical tests. So the reason why people take this this focused approach is the incredible complexity of cancer. Maybe next slide. Yeah, why not just sequence the whole genome of the tumor and derive conclusions from that? And the problem is that when you do that, next slide, when you do that, you get something like this. This is a paper published maybe 2 or 3 years ago, and it shows the results of sequencing a lung cancer, small cell lung cancer, and it's actually the comparison of the sequence of DNA in the tumor compared to the DNA from a normal cell of the same patient. So it's really, well, it should be cancer-specific differences. And the problem is that there is an enormous amount of differences. You have lots of insertions, you have lots of deletions, you have lots of substitutions, you have copy number changes, small regions that are amplified or that have disappeared. You have rearrangements inside chromosomes. With the green lines, you have rearrangements between different chromosomes. You have a whole zoo of alterations, and you don't know what is important and what is not so important in this. Next slide, please. So actually, in this tumor, as stated in this paper, there were 22,000 substitutions. As the authors wrote, 1 mutation for every 15 cigarettes smoked, because this patient was a heavy smoker. I mean, it's a pretty good deterrent. Every time you smoke a pack, bang, you have 1 mutation. And when you have enough mutations, you get sick. And so you don't know which of these mutations are drivers, are really driving the cancer, and which of them are just happen because the cell is just all messed up. So it's better to have a focused approach. Next slide. So for example, it is known in many types of cancer that one of the drivers of the cancer is often a kinase, an enzyme which adds phosphate, which is deregulated. And there are indeed a number of drugs that are kinase inhibitors that inhibit the specific kinase that is overexpressed in a given cancer. And so if by doing this sequencing you find a mutation in a gene coding for a protein for which there is already an inhibitor, you know that this is a drug that is likely to be effective on this patient at this stage of development. So next slide, please. So as I said, this is already in clinical practice, and some companies are offering this type of test. This company called Foundation Medicine using next generation sequencing because you need a lot of DNA sequencing. You couldn't do it by conventional methods. So their test looks at 200 cancer-related genes. They can actually prepare the DNA corresponding to these genes from a sample, even from a sample that's already been put into paraffin blocks, which is what is usually done in hospitals. And they sequence it to very high accuracy. They read each position 500 times to be sure of the results. And from the experience they have so far, they found several what they call actionable mutation. Actionable mutation means a mutation that tells you that there is a possible therapy, tells you that there is an inhibitor for what is caused by these particular gene alterations. So they do get useful results in most cases. They do the test in something like 2 or 3 weeks, which is not too long. And as you see, the cost is fairly high. It's very high for a genetic test. But on the other hand, when you know that a typical cancer treatment may cost $50,000 or $100,000, and that by doing this you're going to use the right treatment for the right patient at the right time and avoid unnecessary treatment and unnecessary side effects, it's certainly quite worthwhile. So this is an approach that is being quite widely used. Maybe in the future, people will do whole exome when it becomes cheap enough to make sense, but at this time this is widely done. Next slide, please. And so the third type of application, well, of course, these applications are not completely different, but they have some specificities. Again, this focused on known mutations, so-called Mendelian mutations. As you know, there are at least 1,000 genetic diseases that are caused by a defect in a single gene. I mean, a different one for each disease, but and in which we know which is the gene. Each of these diseases is quite rare, but collectively they account for, I think, something like 2% of births. So usually when you have a child with such a disease and you don't know, well, you only have you don't know which gene is involved, you make a guess, you have a genetic test, and you find whether it's confirmed or not. And there are, at this time, there are many such tests on the market. The next slide, I think, shows that. This is the growth in the number of DNA tests available in the United States. So it's now more than 2,000. So each of these tests looks at one specific gene, maybe at several mutations in one specific gene for a given disease. A typical one is cystic fibrosis. So cystic fibrosis, we've known the gene for almost 20 years now, And we know the 40 most common mutations in the populations in the US. So one of these tests on the DNA of the patient, if you have a patient for which the symptoms tell you that it's likely to be cystic fibrosis, then you test these 43 mutations and it costs you $3,000. And if you don't find any mutation, then you have to have some other idea, do some other tests. And so in some cases, you end up spending a lot of time doing test after test and not having any diagnosis. So given the current power of new generation sequencing, it's of course tempting to try to do all the tests or a number of tests immediately. And I think I have examples in the next slide. So actually what you can do, you can either have specialized panels, so a test that looks at all genes possibly involved in severe combined immune deficiency, or all genes possibly involved in heart problems, or all genes possibly involved in deafness, or many other cases. Or you can actually try to look at all, almost all known Mendelian diseases. So that I think I have examples of these two approaches. So this is again offered by a company. It's called Children's Mercy Center, but it is a commercial company. And so here you have the cases, what they say about the cases in which this kind of test is likely to be useful, basically where there is evidence that it's a genetic disease. Many tests have already been done without conclusive results, and suspected diagnosis would change treatment, of course. And I think the next slide shows one of their panels. So this is their so-called comprehensive SCID panel for immune deficiency. So they've assembled they have 18 genes known to be involved in some immune deficiencies. And so if you send the DNA, they will do the tests they will sequence all these 80 genes and look for mutation, and it will cost almost $4,000, but again, it may be quite worth it. And again, this is only possible because you can do a lot of sequence without spending too much time and too much money. Next slide. So in this case, that company, the name, as you see, is Good Start Genetics, and they advertise the similar tests for a large number of mutations as carrier screening, which means prospective parents before they conceive a child check that they are not both carriers of mutation in the same gene. So I'm not sure what I have after that, but this approach has been used in one specific case within the Ashkenazi population. Maybe we will come to it. So this is another possibility. Next slide. And this is maybe a more advanced test. This is again by Children's Mercy Hospital, and as you see here, they've been able to set up a test that looks for genes involved in almost 600 rare childhood diseases. Again, these are all monogenic diseases where there's a single gene involved, and this gene is known. And I think I have one example of using this test. It was actually not used as a carrier screening before having a child. It was used to diagnose children with a severe problem. So again, this is the case. You have two children with severe ataxia problems, uncontrolled movements, and these kids had already been through several years of DNA testing, spending a lot of money and not finding mutations in any of the 4 or 5 genes that had been tested. And so using the test that was shown in the preceding slide, a mutation was found in a gene that is known to be involved in movement control. And it turned out then by sequencing, doing this, running the test of the parents, that both parents were carriers. So they were both heterozygous. They had 1 copy of the mutated gene, 1 copy of the normal gene, so they were normal, but the child had inherited, the 2 children had inherited the 2 non-functional versions of the gene. And it turns out that in that case, knowledge of the gene involved suggested the treatment with a drug that was effective. So again, knowledge in that case led to more effective treatment. Okay, so as the examples I've given show, this is a way to do pediatrics diagnostics to avoid so-called diagnostic odysseys, which lasts 4 years, test after test, and no gene found and no treatment can be effective. Can be used for carrier testing for future parents. And some people are talking about extending it to systematic screening of embryos in vitro fertilization. You could imagine that you test many genes in embryos produced by in vitro fertilization before implanting one of these embryos. It is already possible to obtain a complete DNA sequence from a single cell, so it is possible to do that. Whether one should do it is another question. Okay, next slide. So, of course, in all this one must, there are a number of issues about the quality of the sequence, whether you can really trust the sequence when you find a mutation, you really test it with the gold standard method, which is a lot slower and more expensive. There's a trade-off between quality and cost, but I will discuss this in detail. There's also a lot of work to be done on the interpretation. You cannot spend months of informatician time to understand each case. You have to have good programs that produce results that are clearly understandable. In the clinic, the time factor is often critical. You cannot wait 3 months for the result. You need, if you are using this for to guide treatment, you need things to be done in a regulated environment. In the USA, it's the so-called CLIA environment, and then you need to handle the cost and the reimbursement of these tests by insurance companies or by the national health system. So actually, this is really being worked out. The next slide shows a few news items showing hospitals or centers that have started using new generation sequencing in actual clinical practice, and that are working out the details, the procedures, the administrative handling to really put it into full practice. Okay, finally we come to the ethical issues. Yes. So probably the major new feature that comes up is so-called incidental findings, meaning you're looking for one thing and you find something else. And this has impact on informed consent, and it falls into the general issue of genetic privacy. So I'm going to discuss this in the last 10 minutes or so. Next slide, please. So this is, well, an example of incidental finding. You have a baby girl with signs of mental retardation. You have some reason to think that this is genetic, maybe because an older sibling was also mentally retarded. Anyway, you end up sequencing this girl's exome, and actually you find that she is carrying a mutated BRCA1 gene, which means she's at high risk of breast cancer, which means that maybe among her sisters or extended family, there are also people who are carrying this mutated gene and who don't know it, but who should know it because it's important for their healthcare. So you found something you didn't expect. What do you do with it? Whom do you tell? Who has the right to know? Who has the right not to know? So of course, as I indicated in the next slide, this is not a completely new problem, because even in conventional testing, you sometimes find things that you were not looking for. But with new generation sequencing, you get easily 1,000 times more data than usually. So that means that incidental findings are going to be present all the time. Every time you do one of these diagnoses, you may find what you're looking for, but you're always going to find things that you were not specifically looking for, and you will have to deal with that, to know what to do with that. And that means that the people whose DNA you sequence should know about that beforehand. When they agree that you're going to sequence their DNA, they should know that unexpected things will be found, and they must have decided beforehand what they want you to do with it. So next time, just extend a little the question. So will the incidental findings be reported? Then which incidental findings do you report? Do you report only things that you are sure have very serious health consequences, or do you report things which are a little more shaky, or do you report more or less everything? And so how much counseling do you need to make the patients understand what's involved before they sign the consent form? Or how long is the consent form? Do you end up with a 90-page consent form? And how much counseling do you do once you get those unexpected results to explain what they mean and what they don't mean to the patients? It's also an important question, because the DNA, you sequence DNA, except for a cancer patient, you sequence a child's DNA. This is permanent information. This sequence is not going to change. But 1 year from now, new knowledge will have been obtained. And so some things in this sequence that did not tell you anything today, a year from now may tell you something. So should you reinterpret the sequence every year or every 2 years, and what should you do with the results you obtain? And again, the patients should certainly be aware of that. So it's not a completely new problem, but its magnitude is much higher with this technology. In preparing this talk, I found a couple of recent papers that I thought are quite interesting. Both have someone called Tabova as the first author, were published in American Journal of Medical Genetics in 2001, and there's another one in 2012 about these issues. And this paper is more general, and the second paper is more experimental about the concept form. And I think they list a number of questions when you look at existing concept forms and wonder if they are adequate for diagnostics involving NGS. And also, next slide, this is another table from the same paper that indicates a number of necessary areas of research as we are getting this technology into clinical practice. And I think these two papers are pretty, I don't know if you had a chance to look at them, but they give a pretty good picture. Okay, so of course, a number of people, these institutions that have started using new generation sequencing in the clinic have come up against these problems, and so a number of institutions are working on these problems. There is quite an interesting survey being done by Sanger Institute. I will show something about it. There is a specific project in Germany. There's work from the Presidential Bioethics Panel in the US. There's also been a special call for proposals with almost $6 million funding from NHGRI for research on these topics. So there's a fair amount of activity. Next slide shows actually the Sanger survey. It's actually a survey to the general public. So each and every one of us can access the Sanger website and answer this survey. And it's useful to do it. I intend to do it. As a patient, would you like to know about what pertinent findings? Presumably you want to know, because that's what the test is supposed to look for. But do you want to know about incidental findings? How do you categorize incidental findings? How do you understand risk? Do you want to be able to get the raw data and maybe give it to somebody else for interpretation? What do you consider the duty of the genomic researchers? And so on and so forth. Do you consent to genomic research being done with your sequence? And so on. So there will be, I think there will be quite a lot of also of ELSI activities around this topic. Next slide, please. Okay, just maybe a fun slide, just to emphasize that DNA sequence information is really sensitive information, sensitive in the sense of it reveals a lot of things. This is something that you may have heard about when Obama was running against Hillary Clinton in the Democratic primaries in 2008. Someone managed to get hold of a half-eaten waffle from Obama's breakfast in some restaurant, and he or she, I don't know, put it on sale on the eBay, and he put it on sale on eBay saying this waffle contains Obama's DNA, and so of course the market value of this half-eaten waffle was that you could access, in principle, Obama's DNA, maybe find out if, in the mind of people in the US, if he is genetically a Muslim. This was a big idea, or maybe he has, more seriously, if he is the carrier of some serious disease that might incapacitate him as President of the United States. But just to indicate that in reality, and also more in people's minds, the DNA sequences contains a lot of information. And this is just two examples of tests that are indeed offered to the public currently in the US and in a number of other countries, so-called secret paternity testing, where you don't have to tell anybody, you just send them a used toothbrush, find out if the person who has used the toothbrush is the father of a certain child, and also prenatal paternity testing, where you can actually, from a sample of a pregnant woman's birth, do a paternity testing on fetal DNA, which ends up in the mother's blood, and so find out if, let's say, you, the husband, are really the father of this child that is growing in your wife. So you can imagine the serious ethical problems this raises, but this is actually legal and is being done. So DNA is not just any body part. It is really information, and information is something important. Next slide, please. So this comes to the issue of genetic privacy. Also, once your DNA has been sequenced, you would like this sequence to be really confidential and to be looked at only by the people you decide have a right to look at it. But in practice, this is probably quite difficult to safeguard because, as we all know from emails and WikiLeaks and this and that, files get copied very easily, informatic systems get hacked into. And so some people say that confidentiality cannot be guaranteed. And again, if we think this is the case, then the patients should know that before they agree to have their DNA sequenced. Okay, and I think coming to the last slide, or almost the last, okay. All the insurance issues, of course, will the insurance pay for the test? Will they get the information? Will they use it? Will they end up denying coverage, as has happened in the past? We spent a whole seminar talking about that. Next slide. Yes, another cartoon. So you have DNA, a roller coaster ride for science going very fast, and bioethics trying to keep up. Next slide. Okay, that's the summary slide. So this is really a revolutionary technology because it's only a quantitative improvement, but the quantitative improvement is so huge that it really changes the nature of things. It's one case of quantity, quantitative changes producing qualitative changes. And the applications are really beginning. There's still a lot of choices to be made, many issues, new ethical problems. Which we all have to work on. And I think my last slide is just thank you and tell you that we live and work in a very beautiful place. You should visit us. This is the view from my new flat in Marseille. Wow. The swimming pool is not mine. I prefer to swim in this waters, I guess.
Okay, thank you, Professor Jordan, for your very informative, intriguing, and stimulating talk. So we are now open the floor to everybody for discussion and question.
Yes.
Do you have your DNA be sequenced?
I would say I wouldn't mind. But I don't feel a great urge to have it done. But maybe if I was 25, I would feel differently. I feel that okay. I'm in the last third or quarter of my life, and I have had my children and my grandchildren, and I've lived my life.
But I think your sequence should be your genome should be sequenced because you have we have known what more you done in your life, so we can have the search from the genome, right? And find some association. So I think we should be rather sequence for the people who are going to retire or go to the heaven, so that we can have a retrospective, cross-examination with their past behaviors or events.
I mean, if I was approached for being sequenced in a project that I think is scientifically interesting, I don't think I would mind. Yes. As I said, I don't have I have a number of problems behind me rather than in front.
Thank you.
So would you make your genome sequence available to the public? Also, the second follow-up question, in the case in France, would that be legally acceptable to make the genome sequence available to the public?
Okay. I would hesitate to make my DNA sequence available because of my children. I mean, I would have to check that they agree with it. I think currently in France it would not be legal because, well, normally in France at this time sequencing would come under the heading of genetic tests, and this can only be done for medical reasons or for in the framework of criminal or civil investigation. So I don't have the right to send my DNA to a lab for sequencing. This has a 3-year prison penalty and €750,000, although it's never been done before. That's special.
Further questions? Okay, please.
You brought up the big problem of incidental findings. And you mentioned that it comes up anyway in practice without DNA sequencing. My question is the way doctors have dealt with incidental findings in the past, will they be able to apply that to the genetic problems? Or is it just so much more information and new information that we'll need new sorts of guidelines about how to deal with incidental findings?
I don't really have extensive, I haven't seen an extensive study of how people have dealt in the past with incidental findings, but my understanding is that this is something that has come up from time to time and that people have dealt with more or less on an ad hoc basis. In some cases saying nothing, in some cases saying everything, depending on the MD and his relationship with the patient and the personality of the patient. And the point that's made by a number of people, which I wanted to make here, is that this is going to be now very common, so there has to be some systematic way of dealing it. Otherwise, there will be lots of unevenness and deviations. But no, I don't know if this has been studied seriously by anybody, how it's been done in the past. I suspect it's also not being recorded generally.
I'm curious and interested about the Ashkenazi panel. So the Ashkenazi panel for DNA diagnostic.
Yes.
Okay. So I'm aware of the few genetic disease that is more common in Ashkenazi Jews, for example, some of the lysosomal storage disease and also the BRCA1 mutation. The reason I'm curious is that I'm aware that there are certain genetic diseases that are more common in certain ethnic groups in Taiwan, for example, Kejia and Hakka. They have a higher incidence of G6PD deficiency and some of the blood disease, for example. I just don't see how this could be done in Taiwan or in a specific group that because people always worry about stigmata, that tax associated with a certain group of genetic disease. So I'm just curious how these Ashkenazi panel come about and become commercially available and acceptable.
Well, the Ashkenazi case is a very special and interesting case. So the issue is a disease called Tay-Sachs disease, which is a horrible neurological disease where the kids die at age 1 or 2 after a life of suffering, short life of suffering. And this is a genetic disease, recessive disease, so it manifests itself if both parents are carers, in average 1 child out of 4, and it's actually highly prevalent. It was highly prevalent in the Jewish Ashkenazi population, probably because it's a recent mutation, maybe which has not spread outside this particular population. Also, this is a very close population because of religious and community rules. So the frequency of this disease, the frequency of the mutation and the frequency of the disease was very high in this population. And already 20 or 25 years ago, there was a test, which actually was not a genetic test, it's just the test of enzyme level, which is lower in carriers than in normal people, but has no effect in the carriers. And so this community set up a system in which all children of school age were tested, but they were not told their results. The result was given to a kind of central office, which has a name which in Yiddish means good life, something Dar Yeshiva. And so this central office has the records for all the kids. And so then when a man and a woman or a boy and a girl are contemplating marriage, then they interrogate the central office. And the central office say, yes, you can marry, or say, no, you cannot marry. And of course, this works in this particular community because it's a very close community. People don't have children outside of marriage. If they're told not to marry, they do not marry, and so on and so forth. But it's an ingenious solution because it avoids telling people that they are carriers, unless they happen to choose a partner who is also a carrier, but that's going to be very uncommon. So it avoids stigmatizing the people who are carriers, as has happened with other diseases in the past. And yet, it has resulted in almost complete disappearance of cases of Tay-Sachs disease within this community. So it's been very successful. And so then on that basis, people have developed what they call acid panels that test on DNA this time, not only for Tay-Sachs disease, but for a couple of the other diseases that are more common in this population than in others. But it's really an ingenious solution to the problem, but one that is not going to work in an open community. You might call it eugenics, of course. That's another discussion.
Any further follow-up on this question?
Yeah, I can actually add on a little bit. About the action.
Because I was trained at Sinai Hospital at Jewish Hospital. Actually, they are more ingenious than what Professor Jonah has told us. The rabbi actually assisted in this kind of new eugenic activity for getting them wrong. They actually discourage people to date, so they do one step further, not to discourage people to have a child or marriage. They give the kids when they are adults, and I don't know at what age. So my point I want to raise to the socialists to discuss is how in Taiwan a religious institution like very powerful Guangsan or Sisi, they actually implement into medical practice. For example, they are very powerful in helping setting up the HLA matching system. So if we want to advance our genetic or genomic practice, I think this is a good way to work together with the community in an effective way and in a positive way. This is my reflection and my comment.
But I mean, of course, the idea is that if you do, let's say, in the future, maybe everybody will be sequenced at birth, so everybody will carry around his full DNA sequence, and before they decide to have a child with somebody, they will test the two sequences against each other, and if there are risks of genetic disease in the offspring, then they will do in vitro fertilization and check the embryos. They will do pre-implantation diagnosis. So of course this is a solution for a rich society, but it's workable.
So, Bertrand, you will see the progress. It happens this way as a beneficial outcome, because we can actually avoid harm by knowing and also manipulating the operation together with assisted reproduction.
So, of course, this is the bright side.
Yeah. So I think the movie in the Gattaca scenario is quite close to become reality.
Yeah, that's really impressive, because when that movie came out, I think it was in 78 or so. 97. No, 97, yes. So it was just the beginning of the Human Genome Program. It was underway. And in the movie, I've seen the movie. In the movie, people pass through kind of how do you say, like in the subway, and their DNA gets analyzed as they pass through, and then this seemed really far out 10 years ago or 20 years ago, and now we're almost there. We're at the point where my genome can probably be analyzed in, let's say, 5 hours. So we've gone from 10 years and thousands of people and billions of dollars to 5 hours and a few $1,000s. So who knows where we will be 5 years, 5 or 10 years from now.
So Bertrand, could I come back to a few points?
Yes.
The idea is quite eye-catching. Okay, so confidentiality cannot be guaranteed in the electronic age. I think will be more and more so in the future. So the Obama scenario you used actually has been mentioned before, but it was maybe 10, 15 years ago. It was Ronald Reagan. Okay, so people saying that Reagan later developed dementia, so he might have some dementia gene. But in earlier time, when he was having a dinner with someone else, so if anyone can get hold of his napkins, okay, before he was elected as president at that time, okay, they at that time analyzed his sequence and say that this gentleman actually had a dementia gene. So when he will become a candidate of U.S. president, this information could be quite harmful for him, okay, because you will reveal that maybe these people who will become dementia is actually running this presidency. So this will be a harmful information. And it is certainly wrong if the information was used like that. But in the future, the reality will be that confidentiality will be more and more difficult to safeguard. And okay, I noticed that some commercial-based health sector in Taiwan, for example, sponsored by Guotaimin, okay, they have built some health examination center. Okay, so they provide this whole genome study or genome-wide study for who can afford to. So maybe later we can have some package just like an ID, and this information could be electronized and maybe incorporated into our IC card. And if it is more clever, it will be used combined with some RFID device. So when you have this RFID, radio frequency, something like that. So we know this technology is quite advanced in some places. So when you enter certain shops or building or department store, they scan you and they know about this information, and they then further know about your sequence or some special trait. So this information could be very useful for business, but also maybe useful or harmful for other purposes. So the problem is that if this always happening, okay, how can we really safeguard the genetic privacy? I know that in UK they have a law called DNA theft. Okay, if you are not allowed to do that, okay, even though you know that this material is quite valuable. just from the pancake, okay, the waffle, or from a napkin. But anyone who dare to take this sample and make it some certain purpose and use, it is a criminal. Maybe you have the same law in France. So the issue will be that if the confidentiality is difficult to safeguard, and the way to counterbalance this fact will be that you have certain very thoughtful rule. If anyone violates this genetic privacy, will be punished. So could that be some kind of safeguard or some necessary mechanism in this area? So this issue. You and
well, maybe I would like to make a remark which came to me while you were phrasing this question. We have to be careful because actually in this talk and in our discussion we are taking a biased view of determinism from DNA, because we've been looking, and all these companies are looking at the easy thing, which is monogenic diseases. I mean, diseases that are caused, genetic diseases that are caused by a defect in a gene, always the same, Mendelian diseases. And these are the easiest, of course, because they are simple, relatively easy to work out, and you know that you have to look at just one gene. But then we tend to forget that most common diseases, I mean, like diabetes, hypertension, so on and so forth, they have a genetic, or autism, they have a genetic component, sometimes a strong genetic component, but that component is mediated by many genes, 50 genes, 100 genes, and we don't yet know all of them. So actually the predictive power of DNA sequencing is not as high as we tend to assume, and the public tends to assume, because our view is biased by these highly deterministic diseases. And there has been actually a very interesting paper in Science Translational Medicine recently, where they tested this assumption using just looking at the similarity in the medical history of real twins, of monozygotic twins. So monozygotic twins have essentially exactly the same genes, and so the extent to which their medical history is similar tells you how much the genome is responsible for the individual's medical history. And the conclusion is that there is actually a lot of difference. So that even if we had perfect knowledge of the genome and perfect knowledge of how the genetic influence happens in diabetes or in hypertension, there is so much from the environment that we cannot predict very much. Okay, I thought it's important to make this point because we tend to forget it, and certainly the public tends to forget it and tends to think that if you have the DNA, you know everything. This is not true. We don't know anything because we're still ignorant of many of the aspects of how the genotype goes into the phenotype. And also it's not true because there's a lot of things that happen between genotype and phenotype. So now to try and answer your question, it's a problem of legislation. The law has to say what's right and what's wrong. On the other hand, some laws are very easy to break, but it's still important to have a law even if some people break it.
Further questions? Please. Concerning the bioethic, concerning the bioethic, do you think there is a difference between European people and Asian people? Or even the European people, maybe Anglo-Saxon and France, is different. But we Asians more pragmatic or more conservative bioethic? Or what is your impression?
I think there definitely are strong differences. I'd like to make two comments to your question. One is the difference between, say, the US attitude and the European attitude. European, generally, I mean, not only in France, but that's also true in Germany, UK, and so on. The attitude towards, for example, towards healthcare is very different from what it is in the US. It's more towards collective responsibility. People find it more or less normal to pay for national health service, even if they are in good health, and in fact they are paying for people who have health problems. They see that as something, kind of solidarity. It's part of the European welfare state model, which of course is in difficulty right now, but it's still quite present in the mindset. In the US, you find many people who don't see why they should pay, why they should be forced to take health insurance if they are in good health. They don't want to pay for the people who are ill, and they feel that they are responsible for their own health. They don't want government to interfere with their life, and they oppose, even scientists like you and me, they oppose Obama's healthcare system, which to us Europeans seems like a really minimum common sense thing to do. Now concerning Asia, I must say so far in the contacts I've had with ELSI people in Taiwan, I've been a little disappointed that there's not as much difference as I would have expected compared to the US outlook. A lot of the ELSI discussions in Taiwan don't have a strong, to me at least, they don't seem to have a strong Chinese flavor. Because I think that the Chinese philosophy and attitude is a lot less individualistic than the American attitude, but it doesn't seem to influence specific discussions about genome ethics and so on so much. And so maybe, well, at the beginning of the ELSI program in the NRPGM, I remember we had those symposia where people presented their results, and the first ones, maybe in 2001, 2002, we had Chinese philosophers talking about Confucius, and which was really disconnected from genomics. And in fact, they were talking in Chinese and presenting posters in Chinese, so it was very difficult for me to follow. And then it moved into discussions in much more familiar terms, but maybe too familiar terms. I would like to see more different cultural flavor to what I've heard so far. So I'm sort of complaining.
Yeah. Well, I probably can add a little bit comment on this phenomenon. I think the former ELSI scholars, people in Taiwan, when they joined this research program, I mean maybe 10 years ago, most of them were trained in the Western country. So the methodology, the issues, the article they Google, I think is mainly the Western based. But the society is also changing rapidly. Okay? I think it's probably a common phenomenon, maybe in Taiwan, probably in Korea is strong. Okay, there's a strong tendency to catch up the world trend, and there may be some difference between Korea, Taiwan, and Japan, because Japan at the same time very modernized, okay, in the technology. But we know that in Japan there are certain traditional cultural barriers are very strong in their social reform. So there's an interesting phenomenon. Yeah, I can understand the disappointment, but you should have told me this 10 years ago, or let the local scholar know. I think the case in Korea is probably more westernized because of the entire problematic or the how can I call this, the national personality want to be acknowledged internationally or even taking the lead. So regarding the Western standard as probably more admirable to be pursued.
I think the actually so-called Chinese, is very practical. It's race, right? So if I think the most people who do the trading very well. I mean, is one is Chinese, one is Jewish. Okay. So I think, as far as I know, many people, many professionals who devoted to DNA staffs around us was very eager to get rich. So I think I think the whole the core value in Chinese culture is to get survive and survive well. So I think they actually in Chinese culture actually of course we have all kinds of more things, more talkings, but actually they are very practical.
Any further comments or questions?
Well, I think if those sequences can be very cheap, and I think they'll have to be good help, a bigger help. Say like now we have breast cancer becomes the #1 incidence, female cancer in Taiwan. Okay, so and that's a global trend. Okay, so now each year we have 8,000 fresh cases of breast cancer cases. Okay, but nobody knows how many percent of them have carries the BRCA mutations. We estimate maybe from 5 to 10 or something. But I think the first we should do to prevent breast cancer is we should catch the high risk group. So I think every woman with newly diagnosed breast cancer, we should check their BRCA genes.
Yeah, and this is not done systematically?
No, actually, the breast surgeon here is not interested in this kind of things at all. So, but actually, from the experience of Ashkenazi, New York, family history that's not a good predictor of BRCA mutation. So I think if those things can be done very cheaply and effective, I think the first thing in Taiwan you should be doing is all the newly diagnosed breast cancer patients should be offered rapid sequencing of their BRCA genes, and if they are positive, and of course BRCA gene positive breast cancer has special clinical manifestations, and also their relatives can be tested. So I think another thing I think we should be doing is ADPKD genes. Taiwan was very famous for our highest incidence of hemodialysis, renal dialysis in the world. Now, fortunately, we become the second. But I know also the same. In the population receiving so-called renal replacement therapy, 10% are ADPKD. But over the same, in Taiwan, the patient receiving dialysis did not check for the ADPKD genes. Actually, it's if we can get rid of those people who get receiving dialysis because of ADPKD, then we may be able to reduce the dialysis population for 10%. So I think maybe we should be, you know, I think if it can be really, you know, those things should be applied at least for this purpose, then it would be, you know, of big help, and without any, without much basic controversy. So, you know, can you comment on this?
Well, in France, I know BRCA1 testing is offered to all women with breast cancer. So some refuse it, but
What we can, you know, because one is you know,
it's done in violation of myriad genetics patents. It's done within the hospitals with their own technology. It doesn't cost $4,000.
No, I think no. We actually, as far as I know, it's some patent programs.
Yeah.
And also, but I think if we do that BRCA sequencing with this technology, did we have to, you know, I mean, did we offend their patent?
But this is okay. The patent is a very complicated issue, and as you know, it's in the Supreme Court now in the U.S. And obviously all this cheap sequencing is going to change the thing because you could argue that if you sequence a person's DNA, you should pay license. Should have a license from each of the holder of patents on 4,000 human genes, because 4,000 of 20,000 human genes are patented. That's nonsense. So this is going to change somehow.
So, but I hope that those new technology could be used for this purpose. It will be a great clinical help.
But I guess the timing of doing this test, either for the renal disease or the BRCA, is very different. When the newborn, is still very young, are we going to test them? Or when she's already adult, or prenatally?
It's up to it's up to the decision of the family. But at least we can offer them effective cheap way to do this. But of course the choice is theirs. Okay. But if those if the cancer, if the breast cancer patient is BRCA negative, at least we say their relatives are free from this potential danger, right?
Oh, I was just going to comment on the problem of informed consent.
Yes.
Because we know that the informed consent forms are getting longer.
Yes.
And the patients are understanding less. There's been a lot of good research that shows that you test patients afterwards and they don't understand very much. So now, not only do the forms or the discussion has to get longer, but it has to go into social information, like what is the probability that your information will be breached and we won't be able to keep it confidential. And that's not something that doctors and geneticists know a lot about. That's something that policemen and information technology and hackers know more about. So that the problem with informed consent becomes impossible, well, more difficult. So
that's for sure. That's a big problem. And, having been through that, I know that at the time of announcement of cancer, you understand very little. You understand a lot less than you should understand because you are struck and yet that's the time where we need the analysis to be made and we need the consent form to be signed. So I don't know. We cannot just drop the concept of informed consent. It's under severe strain.
So Bertrand, I'd like to grab the chance to ask one final question.
Yes.
So if this is becoming more easy and cheaper, so for those biobanks we are creating all over the world, could it be that someday all the specimens in the biobank, either from healthy people or from diseased population?
Would it be?
Biobank.
Yes.
Okay. Once the sample is there, So could that be just entirely sequenced?
Of course.
Will be that.
Yes. And then the question, do you have to go get retrospective additional consent for the sequencing?
You will.
It will make sense, of course. I mean, sequencing is already providing a lot of information about ancient migrations. It's changing our outlook of how the world was populated from Africa. I mean, it's not changing the big picture, but it's changing a lot of important details. And I mean, scientifically, we need this information.
Are we going to be more happy with those?
Interesting question.
So since we are running out of time, let's get our. Oh, take a picture. Yes, please come over and join us to have a photo with Bertrand. Please come here. Yeah, you can leave your camera there.
Be sure to publish somewhere.
请留步，一起来。
来。The guest.
Got two cameras. This is the first one. Okay. 1, 2, 3, cheers. One more. Okay. 1, 2, 3. One more. 1, 2, 3. Okay.
Thank you.
那谢谢。
教授这边多一点。
这边的。
See you.